Okay, so this is my presentation on electromagnetism. So first we have to explain a couple of terms. So electric potential difference, also known as voltage, is the energy that it takes to move a charged particle between two different points within an electric field. Think of it as the speed the river is flowing, basically, uh, if electricity was a river. And then electric potential energy is the energy that a particle has because of its place within a field but not relative to another point. Okay. And then Coulomb's law states that the force of attraction or repulsion between two charged particles or objects is proportional to the product of their charges and inversely proportional to the distance between them. So you can see that here in this helpful diagram, and that's the equation that can calculate the force for any given particle. An electric field is the radius around a charged particle within which that particle can influence other charged particles around it with physical forces through magnetic fields or And here's the explanation for magnetism. So that was the electricity terms. Also, I should add that the electric potential difference is very similar to gravitation in the way that it works, in that it changes and becomes negative depending on how close or far it is from the nucleus of the field. So magnetic poles. Magnetic poles are this part here. So they're the origin of the field, which always moves north to south. Magnetic fields do. So they're where the most field lines, not a real thing, but it's where the field originates and propagates to form its full circle flowing through those points. So the top and bottom are the poles. One is negative or associated with negative, and the other is positive. And then right-hand rules basically state that current flows this way. If the current flows up, have your hand like this. Current is going this way. The magnetic field comes out this way, out here, so around it, and then the force comes this way, like in this next diagram here. Basically just helps you remember what's going on. And then the other components of magnetism are magnetic fields, and that's the radius around which a magnetic object or flow of current that creates a magnetic field by the motion of the current can exert force on other charged objects. Magnetic forces are the attraction or repulsion between electrically charged particles, electrons, because of their motion. So because of how they're moving, they have a pull or push on each other, and because of how they're charged, that also affects it. Combination. So this is how all of these things work in tandem. So electromagnets run a current of electricity through a wound coil, and that generates a magnetic field because of the flow of current. And you can layer them many, many times and get a much stronger field than you can. I should add, this isn't real, it's wrapped around a magnetic core. It makes a much stronger magnetic field than is possible with ferromagnets, which is very useful for things like electric generators or motors, where you need that field to do some sort of work for you. And electromotive force is the work or energy change that's imparted by a power source on the particles. So it's basically how strong they're being shoved through the wire, and that's voltage in amps. Magnetic flux is the amount of a magnetic field that passes through any object at any given moment of time, and it's influenced by the field strength, the area of the object and the angle of the object, as demonstrated in this nice diagram here. So Faraday's law and Lenz's law. So Faraday's law states that if the magnetic flux through a conductive circuit is changing, then there will be an induced electromotive force, or basically flow of current. So changing that magnetic field moves the electrons around. And Lenz's law states that the induced flow of current, because of the changing magnetic flux, will flow in the opposite direction and create an opposing magnetic field to the initial change in magnetic flux. And Lenz's law states that and it predicts the magnitude but not direction of the electromotive force. And Lenz's law predicts the direction of the electromotive force. So now these are the explanations for all of the devices. So a cathode ray tube, or abbreviated CRT, works by charging electrons with a heater within a cathode within a vacuum lamp, basically. And then that vacuum lamp has a couple sets of magnets. So it has the focusing magnets, which focus it into a high energy beam, and then it has another set of magnets which bend that beam towards any given point, which can be useful for working cathode ray tube televisions. So you fire it at the photofluorescent screen and it lights up where you want it. And if you've ever seen those videos, it's a wave going across because it can't shoot them all at once. It has to shoot them in pieces. So it's just going line for line back and forth. And if you slow it down, you can see. A solenoid is just an electromagnet, but we put a permanently mounted piece of metal in the middle, and when we turn it on, that piece of metal is pulled towards the side that it's attracted to. So that's useful for valves, or they use it on some other things too. Lots of hobby people use it to make robots, and I've seen it on like model airplane videos. They use it to do the control services because it's really easy to do. All you need is electric charge, and that's already present on electric airplanes. And one position is achieved with the electromagnetic field, and the other position is a spring because it just goes in. So transformers and capacitors. So transformers, what they do is they adjust voltages according to the use case. So if you're transmitting electricity over very long distances, you want high voltage so that you get the right amount of carry, because there's an inherent loss in energy through long distances because of just resistance. We don't have zero resistance wires, so it loses a little bit. So transformers work by having a central core that is fully enclosed, and you have two different windings, which is like primary and secondary windings, and they step the voltages up and down by having different amounts of winding on each side. So yeah, to step up, you would probably have more windings in the secondary windings, and to step down, you'd have less. And then capacitors. So what capacitors do is they're basically another way of storing charge other than a battery. A battery stores charge through chemical reactions, which is good for a long time, but it's very slow to discharge. So if you need to store charge for a long time, a capacitor isn't that good because it loses it, but a battery is. But if you need to discharge very quickly, capacitors are much better because they can do it almost instantly, because they don't store it as chemical energy, they store it as an electromagnetic field. And capacitors work by having two charged plates around an insulated shell, and they have a dielectric medium, or like non-conductive, in the middle of them. And it creates a potential difference between the two of them, meaning that there is, a voltage being stored, ready to be transferred at any moment. how generators work. So generators work based on all of the principles that I've just explained. All of the electricity principles, those are all just assumed. So those are the base, and then Faraday's law and Lenz's law are the ones that really are what explain how generators work. So a generator works by spinning a coil within a magnetic field. So you spin a coil of windings, and then those windings go out to the brushes, and the brushes transfer the current to the delivery, to whatever work you're trying to do, whatever it is. So basically, you just change the magnetic flux by spinning it with a rotating shaft, and you can do that many ways. Nuclear reactors do it with steam pressure. Dams do it with the flow of water spinning turbines, and generators, what we call it, they're all generators, but like your typical like camping generator does it with a gasoline engine, and that changing magnetic flux induces a flow of current, and we pick it up with what's detailed here: slip rings and carbon brushes. And this is deceiving here, because this makes it look like we're using ferromagnets. That's not how they do it, because the field is much weaker. So these are both electromagnets. How motors work. So motors are the exact same thing as a generator, but instead of rotating the coil to induce current, we induce current to rotate the coil. So that is also done using electromagnets. Again, the deceptive diagram. But basically, for a brushed electric motor, what you do is you have electromagnets on the outside and the inside. And for a brushless electric motor, you can have ferromagnets on the inside, because they don't really need to do anything. They just need to be spun, and you can make a much stronger field around them. And brushless electric motors are alternating current, and direct current motors have brushes. So DC motors work with a commutator, which is needed to ensure a continuous rotation to keep the fields aligned so that they're always pushing in a direction. And all the commutator does is switch the direction of the magnetic field, also the flow of current, basically, because that is what it is. And an AC generator doesn't need it because it produces a rotating magnetic field. Here are my sources.